So let's just zoom out again. Why are we learning maths? And this applies in many respects to coding as well. I think there are three good reasons. Technical jobs that are so driving our economies. Most of the people who lead major companies now are somewhat technical. That wasn't true 30 or 40 years ago. They were lawyers. Or PPE students or something like that. We still have that problem in government, unfortunately, except in Germany. The second reason is, everybody's lives, just to work, just to function in today's life. You've got all these statistics bounced at you. Everything's very quantitative. You kind of got to have an idea of how to function, which, again, you didn't need some decades ago. Thirdly, what you might call logical mind training. Being able to somehow understand how to think about the world, problem solve in some logical way, and, abstract things, turn things into algorithms or procedures. Those are very vital skills, even if you're not explicitly using them for maths or coding. Next question, what is maths? When you're doing maths, what are you actually doing? Well, I think it's sort of 4 steps. It's define the question first. If I close all the rooms, we turn all the air conditioning, if it has it here, off, and I talk for too long, how long can we survive? That would be a question, hopefully not one I'll try and experiment on. The next step is we might take that and translate to maths. Now this is the sort of abstraction point. You want to, why do you want to abstract? You want to abstract because you can take all sorts of different circumstances and turn them into this great language of maths, if you want to call it that allows you to compute answers. Hundreds of years of knowledge on how to do that. Then the third step is you take that question and you find the answer. You compute. The fantastic, magical step of computation. And the fourth step is you go back, you de-abstract. You say, well, x was 3. So maybe we have 3 hours to survive, and you check whether it makes sense. You verify it. If it came out as -4, it was probably wrong. Here's the big problem we've got. Almost all of maths education involves spending our time on step 3, which is drowning out these other steps. And particularly step 2, that I think is so vital, the abstraction step, which is so what's lacking. So what we need is to use computers much more for step 3, and use students much more for these other steps. And, you should think of maths as this sort of problem-solving process, where you're kind of going up this helix, effectively, and you might have to iterate several times round this thing, and eventually, when you've got an answer you think sufficiently good, you've succeeded with your 3D infinity. So maths is a much bigger subject than calculating, and as we all know here, computers do calculating rather well, and we should not have humans try and compete with computers on calculating because they'll fail. So here's an example I love to show, which is to take something everybody has to learn how to do, solve linear equations, and I've managed to set a variable. That's stupid. So let me get rid of that. Okay, start again. Okay, so there is my solution to my linear equation. The thing that, we might end up with a problem that actually just isn't linear, it just happened to be cubic, for example, and then you get a rather harder result. And one that most students couldn't calculate even after years of trying. And it actually gets worse than that. A demo I like to show, Siri willing, is to try and talk to my phone and see if we can do the same thing. Solve x cubed plus 2 equals 2y, and y minus x equals 5. Now, as I say, it's a bit dependent on Siri, and Wi-Fi and everything else. But okay, so we got it. Let me just turn my camera on here and try and show you. So there we are. There is, out of Siri, my cubic, all with a nice Argand diagram produced by Wolfram Alpha. And as I like to show ministers of education, if I can talk to my phone in 20 seconds, you've got to be asking why we're drumming people through 10 years of this stuff so that they can't even do that. Now, one thing people say is you've got to get the basics first. And presumably most of these people saying this mean you've got to learn how to do stuff by hand before you do them on a computer. I think the basics are learning how to do that 4-step process really well, including the abstraction, including how you abstract to getting a computer to do it. That's a very core part of that. And, it's like, are the basics of driving a car learning how to machine a piston? don't really think so. I think it's driving as a rather separate subject. If I want to figure out how fast I can drive my car around a corner without it skidding off the side, I could go and work out all the dynamics of how it works, but realistically I need to get experience of how to do that and kind of when it's going to leave the road. That's much more useful than working out all those detailed things. Another thing goes wrong, I think it very much relates to the point of how we fit it in other subjects, is current maths is all connected with the mechanics inside. You know, completing the square, or my particular dislike simplifying surds, if I can remember what they are. The mechanical bits, the bolts. What we really need is to have problem-centered maths. Yes. And, you know, these are some of the problems we like to try and have people do. Design a currency, it's a primary thing. What coins and notes do you need to be able to get every denomination? I'm going to the US later today. You know, they have 25-cent bits. It always seems to me weird, but it's kind of amusing as opposed to 10 or 20p pieces. You know, how many levels of friends are we separated by on Facebook? What's a perfect password? Are girls better at maths? Give them all the data, get them to figure it out. See if the girls can game it to be different to the boys. What's a beautiful shape? That's a perfectly valid maths question. You know, the Greeks worried about that. Why can't we have that as a question? These are all fairly open-ended questions, and they need a fair amount of computing to make them actually work. So one of the messages I have, and I think you as a group absolutely understand this, is more practical is more conceptual. Governments love to talk about the vocational versus the intellectual. Actually, in the modern world, those two have converged rather heavily. And the things that are practically useful to most people are also, in fact, quite conceptual, because we have machines that do lots of the more tedious stuff. And so, you know, a lot of these things like abstraction, which are hard, conceptual things, are actually heavily practical if we do them right. The thing about abstraction is so bizarre, because in maths, we teach it all backwards. You guys are teaching it forwards. Okay, which is what so what I mean by it being backwards is in maths we say, you know, go and learn how to solve a quadratic equation. And there are all these weird symbols and you do all this formula stuff and eventually come out with a number. And if you're very lucky after you've done that, you know, 1,000 times, you might be allowed to try and apply it to something. By which point most students are, you know, asleep. And the few that like it didn't really want to do a quadratic, they want to do a quintic or something. So what I think you ought to do is you know, the abstraction is a tool. You have a problem. You want to use maths to solve the problem-solving process of maths to solve the problem, which involves abstraction. You then want to take that and use, you know, computers to calculate the thing, you know, the calculating bit, and get the answer. So we should use problems, and we should use abstraction as the power, not the ability to stare students off. And the most bizarre thing, this very much connects with the first talk. It's so bizarre, but if you remove the computer, you will remove most of the context from maths. Why do I say this? Mathematicians hate me saying this, but the fact is maths wasn't that useful for most subjects before computers. Right? It was good for bits of physics, it worked well for that, it worked well for some sort of things like accountancy, but it worked terribly for things like biology, messy, big data, all of these sorts of things. And arguably, it didn't work great for complex finance, but then arguably it hasn't since either. So that's a different problem. That's an educational problem. Anyway, so the point is, it's no good setting people in maths biology problems, biology word problems, if there's no computer, because the problems are going to be toy problems that don't make a lot of sense. Nobody used maths for doing biology, really, before computers. You need the big messy problems, lots of data points, lots of stuff happening, lots of mess, lots of hair, so that you can attack real problems that they can see are real problems, not some weird sort of simplification of that, have the real hair in them. You then need the computer to be able to actually do that. So if you remove the computer, far from sort of elevating the subject to more conceptual, you actually remove much of the conceptual element. And people, for some reason, often fail to understand that. So, key point, in order to do real STEM today, any of those subjects, you need to be able to code. And I actually think coding is in many ways a more central thing even than governments and things think it is. Because I kind of think it's the way you write down that step 2, that abstraction step. Both the writing of it down and it's getting the computer to actually do it. Here are a few little examples. I think it's great that you can kind of play around in thermodynamics with, make a little app here which works, and you're changing the temperature. Actually, there's a little bit of artistic license as the color changes with the temperature, but never mind. And it's actually computing this live. It's kind of cool that you can just make a little app to do that. And, and then you could even show the theoretical value and notice that when you suddenly change things, it doesn't meet the theoretical value initially, etc., etc. Here's one I like to show. This is one where we've divided the class assignments in two, and we tell half of them to toss a coin and note down the results, and the other half to cheat by doing what I'm going to do, which is to sort of do, type stuff in like heads and tails, as if I'd done the experiment but not actually do it. The question is, when you hand all results back to the teacher, can they tell? And the answer is usually yes. So if I take that, you'll find that my cheating only passed one of the 5 tests. So it's pretty obvious I cheated. Now let me do a semi-cheat. What I mean by semi-cheat is I'm going to, I'm going to make a random, I'm going to get the computer to pretend it tossed the coins. It has a better random number generator than me. So let me do that, let's say 200 times. And we're going to get ones. It looks like we got ones and zeros rather than, let me just go down here. Got ones and zeros rather than heads and tails, but I think the thing I have will. So let me copy that and let me put it back in this, and let's see whether my computer managed to pass. And well, it got 4 out of the 5 tests anyway. Isn't that amazing that a teacher can tell whether you cheated? And then the kids start coming up with lots of theories as to how this worked. And of course, then you get into the patterns of the data, and you explain, well, that's how credit card fraud detectors work and things like that. So it's an immediate thing that they can see. And I think that sort of is a good example of maths and coding and everything coming together. And then they write a piece of code to do that. So the way I think about this is maths is a system. It's a process for doing STEM and life, actually. It's a problem-solving process. And coding is the way to express and execute that process. You've got to, it's no good writing fancy integral signs that we all wrote, very nice. You need to write the code so that the computer can do it. And that's what all of you are very much involved in. I wanted to show a few bits and pieces here. So we have this language called Wolfram language based on Mathematica. And I think we're starting to get this more into schools in particular. We have a cloud version of this. One thing I'd love you to take a look at as you have a chance is when people sort of run out of steam a bit with Scratch. I think it's great. The question is, where do you go to then? And I think we've got a great way of sort of having the maths and the code plugged together here in a way that they can really use across these things and do some things fairly quickly. So let me do something like, interact, let's say, sine x. I don't know if this is going to work, but sine x plus sine nx or something. Is that going to work? I don't know. What I'm doing is I'm throwing a very sloppy thing into it's done the wrong thing here. Let me try interactive or something like that. So trying to throw a very sloppy thing in, get it to write a piece of code for me, which it did. So what we've got here is sort of our alpha technology hooked up to coding. And you can write something very sloppy and actually get a piece of code. It's a great way for some people to start getting the sort of real code. And then, of course, you just click on this and start actually changing the code. So I might say, by the way, just to be clear, what I built here is a little interactive app. And if I just scroll down here, you can see this is a little interactive app I built in one step there. And, I could, for example, add something saying, well, let's put an A on the front there and see if I can, make A go from, 1 to 10 or something. And then if I've done this right, we get a second slider. And, sorry, I'm having a scrolling. Come on, scroll down. Okay, my computer is misbehaving for first time history. But anyway, you can see that as I change that slider and this slider, we get... Oh, actually, I'm just doing something not very exciting here. This was supposed to be a beats example. Anyway, not quite right. But you can see it was really easy to make this little interactive thing and quite easy to understand.
Can you go back about 30 seconds because I got completely lost? Or do you not have time?
So you got lost when I did the interactive typing the text in?
Yeah. Okay.
What I was doing there was I was just uttering English words to try and get some code written. So it was like a linguistic way to write code.
Oh, right,
And so then I said, okay, great, I've got the code I want, the real code, the Wolfram language code, which is this. And now I'm just going to use that, forget about the English I wrote, because that's just done the job it needed to do. And I've gone and generated this, and now I'm sort of into the real syntactic code, so to speak, and I'm going to go and adjust that and improve it. And another thing you can do, which is quite cool, is I could take that last line and, except I can't, so I've done something dumb. Well, let me not try and do this right now, but I could take the, I could take this last line. What I was going to do is cloud deploy this, so you could all pick it up in a browser. Let me. What have I done here? Let me just do something. I've got some weird mapping of my keys so that I can press something, and I've managed to screw that up, which was probably dumb. Okay, so now let's do cloud deploy of the last line and permissions. I want to make the permissions go to public, otherwise you can't see it. And let's do this, and let's make the URL short. URL shorten like so, and then miraculously, if I've done this right, which I may not have done, we get a URL. If any of you type that, it should hopefully come up. It may be a bit slow at the moment. It should be able to. You should be able to view this app that I've just made. Moving swiftly on. So now I'd like to build another little thing. I thought it was the sort of time in the talk where you're kind of fed up with seeing me. So what I was going to do is try and block my face out. Let's see if I can. It's a bit early on a Saturday morning to be doing this, but anyway. So what I'm going to do is code. I want me to be the current image, and then I want to show me at the same time as graphics of, let's say, a rectangle applied to find faces, I think is what I want. And then I want to do that of me. And these things never work as well when you're looking at them. So let's see if, oh yeah, there we go. We got our, so I have managed to combine a find faces algorithm with me. In fact, it's quite nice because even blocking me out on the view of the projector. Now, one thing we want to do is to show that in 140 characters, you can make a meaningful Wolfram language program. And so we set up tweet a program, and the idea is to tweet programs, and people have been doing this, particularly a lot of schools and things, to figure out what you can actually produce in 140 characters. So, of course, you can all go and try this. In fact, I think we put a little thing in your packs with a tweet a program sort of card thing. But anyway, this is just nice to show that what I think is exciting is you don't have to write pages of code to get real fun results. And you can combine them with cameras and all sorts of things. And I think that's a really valuable thing, particularly as people sort of emerge from, primary through secondary and are keen to sort of get further. We've also tried to set up this training thing called Wolfram Programming Lab to get people excited about sort of getting into this with some neat examples and some little piece of code and walking through those. And I hope that's, again, helpful for people to kind of get started on some fun programs. And I haven't signed in, and it's making a big fuss. Oh, gosh, it's one of those morning things. Yes, cloud sign in. Right. The other thing I want to show you, which I would love contributions to, and I think it's quite, is this demonstration. So we've been running this for quite a few years. And as you see, it has over nearly 11,000 interactive demonstrations on it of all kinds. And, I'm just going to I have no idea what I'm picking here. I'm going to pick a totally random demonstration. And these are essentially little Wolfram language programs. And then, they display like so. Oh my gosh, this is a complicated one for sure. This is, oh my God, lishes you patterns on a sphere surface. Oh my goodness. Now, there are ones all the way from primary right the way through to, serious research scientist contributions here. And the cool thing is, this one will be complicated, but you can have a look at all the code, which is available. As I say, this one's pretty complicated, although that's the total code. But it's great to be able to submit these as well. And we've had not only teachers, but also students being as projects, seeing if they can get through our editorial process. And if they do, they pass the project. I discovered one teacher was doing. So it would be great to do that. Another thing I want to show you is that you can pull data. So this one is, let's see if this works. So this is importing the data for Boris bikes in London. And this is a thing which shows where the Boris bikes currently are as it evaluates. There we go. So those are the positions based on how many are in each Boris bike place. And it's kind of cool because you can go and start finding out, what happens over time. I think this was we've sort of submitted this to a data bin so you can kind of accumulate it over a week. And I did that. And then you can get a plot like this to show that, for example, all bikes tend to go downhill over the day because people prefer to go downhill, and then trucks have to go and take them back up to the higher places. It's kind of amusing. And we built a little interface here where, in fact, this code has produced an interface where you can choose a city, and all the cities with bikes. I have no idea whether this will work, but let me try Barcelona. And there we go. There are the Barcelona bikes pulling the open data, and there are the current positions of all the Barcelona bikes. So that's just an idea of how one can kind of use data and mesh it with code. And I think that's kind of fun for lots of students. Now, talking of open, one of the things we were very pleased to do was to bundle Mathematica and Wolfram language with the Raspberry Pi. And so you go use Raspberry Pis with this. And actually, I was at dinner with Eben Upton a couple of days ago, and he was pointing out to me correctly that there are pretty much only 2 times when we've bundled Mathematica with a computer. One was when we launched it with the Next machine, and the Next machine was what Steve Jobs did when he was kicked out of Apple the first time, and he was at our launch event. In fact, he even came up with the name Mathematica. So that and the Raspberry Pi. So anyway, that's it's nice to be able to do that, and it's fun to be able to sort of use it as an embedded system. So look, big sort of message here from my point of view is, which you guys know, but much of the rest of the world doesn't quite understand. When we get new automation in life, we need to make sure we transport that to education, and we don't try and get people to pretend to be machines. If the machines are good and they work, let's go further. Let's work up a level from the machines and not compete with them. And clearly computers are not going away, and that's sort of what we need to do. We want first-rate problem solvers as humans, not third-rate human calculating machines. And I think the work you're doing is very much, absolutely in tune with that. Back to Jobs, actually. I found this quote only quite recently again. Back in '88, he gave us a nice quote for our brochure or whatever. And the quote, but it's a very incisive Jobs kind of quote. So, Mathematica will revolutionize the teaching and learning of math by focusing on the prose of mathematics without getting lost in the grammar. So that's, in my view, a very nice, incisive Jobs way of saying, use the machinery for what it does. Keep your eye on the essence of what you're doing. And I know very much the talk before this seemed, the talks I should say before this, very much had that in mind. You've got to get idea of what the algorithm is, what's the vocabulary to describe. So all of these things are really important parts of that. But don't ever forget that the machinery will change. The machine, what code looks like will change over the next 20 years. That doesn't matter. The idea of making an algorithm probably won't change very much. The way you manifest it will change. So we need to go with the change, but keep the essence. The reason I highlighted will is because, in a way, this was so right and so wrong. It should have said should. We haven't yet managed to do this, but we are on track. One thing that, again, I don't see any danger of right here, but I think we just need to be very careful of. One of the problems that has happened with maths is that it's got this thing where it's sort of good for its own right. 20 people in smoke-filled rooms decided that this was a good thing to do, except they're probably not smoke-filled anymore. I think it's really important to get all the people who use it and figure out what it is that you're supposed to be doing with it in life and work back from that. And I think it's really important as the computing at schools and everything around coding moves forward that we very much keep that in mind and don't turn it into, well, we were very keen on coding and it was very exciting for us. And maybe it's not exciting for 80% of people, but anyway, they should do it. I think it is important for everyone, and I think if we keep that in mind, it will stay focused in that way. So really, I think what's exciting is to build a computational thinking curriculum assuming computers. So what we've done, we've launched computer-based math to try and fix the math curriculum around the world. And we have a very simple idea for this. Assume computers exist and rebuild the curriculum for maths based on that idea. Seems simple, but doesn't appear anybody's exactly done it. And figure out how that obviously fits with coding. Maybe it's even the same thing as coding in the long run, or computational thinking. So I thought I'd end with just, what are some top actions that one could sort of do and think about. Always start with context, in my view. It's a great way to start. And use computational thinking as a solution. Optimize the transition from scratch when students have got to that point. See whether our programming lab, Wolfram language, fits that bill. Deploy all subjects in coding and maths, very much in tune with the first talk. These are horizontal subjects that should empower everything. Just like learning to write empowered lots of subjects, so learning to code and maths empowers lots of subjects. And there's a workshop later on Wolfram language, so attend that. I've been told to say that. So thank you very much.
Don't miss out on Computing at School's great content here on YouTube. Subscribe to our CAS TV channel.